Okay, thank you very much. So I'm going to add another dimension to the challenges that we already have in planet formation and add a binary companion to the process. So since most stars are in binaries, it's an important thing to consider. This is some work that I've done with my collaborators, Steve Lobo at Space Telescope. Alessia Franchini is a postdoc at UNLV. Jeremy Smallwood and Cheng Chen are graduate students at UNLV. Okay, so first of all, to motivate my talk, misalignments between these disks are observed to be common. So this is one example. It's a binary protostar IRS-43. These are ALMA observations. The binary is shown by these yellow points, and the inclination of the binary is within 30 degrees of the plane of the sky. The dashed lines show disks around each component, and this long one shows the disk around both components, the second binary disk. And since we see all of these disks edge on, we know that the misalignment between these disks and the binary orbit has to be greater than 60 degrees. Okay, so a few more examples of misalignments just to show you that they're common, and I'll come back to some of them later. But GG tau, second binary disk, misaligned by 25 to 30 degrees. KH15D, not entirely certain of what the misalignment is, but we see that the disk precesses and it covers up the stars. So we know that the disk must be misaligned. 99 Hercules is actually a debris disk. It's misaligned by 90 degrees to the binary orbital plane. And HD 98800, recently found, is a gas disk that's misaligned by 90 degrees. And just to point out that the eccentricities of all the binaries in these cases are significant. A little bit of background on binary star formation theory. So if the binary stars are thought to form from disk fragmentation, then we would expect the orbital axis of all of the three disks to be aligned to each other. But simulations suggest that this isn't the case. This is a simulation by Matthew Bate. There's a binary at the center of this. Each panel just shows a different view of the same object. And you can actually see there's even two disks that have formed around this one binary. And the disks are misaligned to each other. So these have occurred from different accretion events during the star formation process. So it's likely that turbulence within the cloud actually affects the alignment of these disks. Okay, so let's try to understand the dynamics of the circumbinary disk. So the easiest thing first to understand is the orbit of a test particle. Okay, so we have the binary here. I'm initially just going to assume that this is a circular binary. This is the angular momentum vector of the binary. And we consider a misaligned test particle. So the angular momentum of the test particle is in this direction. So because of the misalignment, we get nodal precession. So the plane of the orbit of the test particle precesses about the angular momentum vector of the binary. And during this process, the inclination remains constant in time. But the timescale for this precession depends upon how close you are to the binary. So the closer you are, the faster the precession rate is going to be in this test particle case. I'm going to explain this phase diagram because I'm going to use it later on when things get a bit more complicated. But for now, so this is I cos phi, where I is the inclination of the test particle to the binary angular momentum, and phi is the longitude of the ascending node, or the phase angle of the orbit. So the distance from the origin in these diagrams is the inclination, and the azimuthal angle around is the longitude of the ascending node. So for this circular binary, the test particles simply just precess with the same inclination. So constant inclination leads to just a circle in this diagram. The green orbits are orbits that are closer to alignment, so the orbit precesses about the angular momentum vector, and the blue orbits are orbits which are closer to counter-alignment, so they precess about the negative of the angular momentum vector. Okay, so what happens if instead of just one test particle, we instead have a disk? So we've already said that the precession rate depends upon the distance from the binary. So particles in the disk that are closer to the binary want to precess on a faster timescale than those further away. But in the disk, each ring of the disk is connected. So there are two ways that it can be connected. First of all, if it's a low viscosity disk, it can be connected through wave-like communication. Or if it's a high viscosity case, then it can communicate through viscous effects. Protoplanetary disks generally have a low alpha, and so we're in this wave-like communication regime. So the precession is communicated about half the sound speed. So if the disk is going to be able to hold itself together and precess as a solid body, so every radius precesses at roughly the same rate, then we need the time that it takes these waves to cross the disk to be shorter than the precession timescale. So if this is satisfied, then we have solid body rotation. If it's not satisfied, the disk isn't in good communication, then this can lead to effects such as disk warping, where different parts of the disks have different inclinations, or even disk tearing. So you see here there's an inner disk that's ripped off from the outer parts, and now each disk precesses on different timescale. But for typical parameters for protostellar disks, it's likely that they'll precess as a solid body. Okay, another difference between the test particle case and the disk is that we have dissipation within the disk. So what this means is we're moving to a lower energy state. And so instead of the disk precessing around the binary angular momentum vector at the same inclination, it instead spirals in. So it moves towards alignment with the binary angular momentum. Okay, but things become more complicated when we introduce some eccentricity into the binary orbit. So this, again, is the same phase plot that I showed before. So I cos phi, I sine phi. So remember, the inclination is the distance from the origin. But this is now for an eccentricity of 0.5. So if we're close, we begin with an orbit that's small inclination. Again, we still precess about this angular momentum vector of the binary. But if our inclination is above some critical, then instead of precessing about the angular momentum vector, we instead precess about the eccentricity vector. So we introduce these new types of orbits. So on the next slide, I'm just going to look at one of these orbits in more detail. So this is an orbit that begins at an inclination of 60 degrees. This shows how it changes in time. And this is the longitude of the ascending node. So we're exchanging the inclination with the longitude of the ascending node during these oscillations. The solid lines show a particle closer in, and the dashed lines show a particle farther away. So the farther away the test particle is, the longer this timescale for the precession. Okay, but the amplitude of the oscillations remains roughly the same. Okay, so there's a critical inclination dividing the two regions between the two types of solutions. So I was just looking at a binary that had an eccentricity of 0.5, and this critical inclination was roughly 40-ish degrees. But this critical inclination depends on the binary eccentricity. So the higher the binary eccentricity, the smaller the critical inclination. So the higher the binary eccentricity, the more likely it is that a randomly distributed disk inclination would actually be librating. So it would be precessing about the eccentricity vector rather than the angular momentum vector. So now back to what happens if we have instead a disk. So as before, around the eccentric binary. So if the inclination is low, the same process happens as before, and it's going to align to the angular momentum vector of the binary. But if our initial inclination is sufficiently high, we can instead process about the eccentricity vector. And as I'm going to show you in my simulations in a moment, this leads to the disk aligning to the eccentricity vector. This is what we call the polar alignment. Okay, so this is the initial setup for one of my simulations. So I'm using the phantom code written initially by Daniel Price. So the disk is initially misaligned by 60 degrees to the binary orbital plane. These three images just show different views of the same object. Have an equal mass binary, the eccentricity is 0.5. It's a relatively narrow disk, so it extends from twice the binary separation up to 5 times. I take H on the disk aspect ratio to be 0.1 at the inner edge, and alpha of 0.01. And here, this shows the evolution of the inclination and the longitude of the descending node. So I show 2 different radii in the disk, 3a and 5a. So you can see this now that this is quite different to the test particle situation. So for the test particles, they process on very different timescales. But because the rings in the disk are connected, the timescale is roughly the same for the whole disk. Another difference between the test particle is that the oscillations are damped. So the magnitude of these oscillations is decaying, and the inclination is converging on roughly 90 degrees. So the disk is moving towards polar alignment. This is the phase diagram for the same simulation. Shows the same thing. So the magnitude of the oscillations is decaying, and it's converging on the eccentricity vector. The reason that this isn't at phi of 90, as in the test particle case, is because the disk has some mass. So in this case, it was 0.001, that of the binary, and that caused the eccentricity vector of the disk of the binary to precess. So the eccentricity vector would be over here somewhere. And this is what the disk looks like after 500 binary orbits. This is the xy plane, so the binary is orbiting in this plane, and you can see that the disk has become very close to polar aligned to the binary. We explored a wide range of disk and binary parameters, so the radial extent of the disk. So if we increase the size, the process still occurs. If we increase it sufficiently, the disk will no longer be in good communication, and this can lead to disk breaking. The same is true if we decrease the disk aspect ratio. Again, we can get disk breaking. The viscosity, this is an example of an increased viscosity, leads to faster damping. Binary eccentricity and binary mass ratio also. So we find it's a very robust mechanism. It operates for a wide range of parameters. We also solved the wave-like warp disk equations from Lubo and Ogilvy 2000. So this assumes that the disk is initially close to polar and that the amount of warping is small. These are both reasonable assumptions. So we ran another simulation, which began at 80 degrees, very close, to compare to this theory. So the top plot shows the period of the precession as a function of the inner truncation radius of the disk. And the simulation agrees very well with this linear theory. And then this bottom plot shows the damping rate, so the rate that it moves towards alignment. Okay, then more recently we've considered the effect of the disk mass. So this qualitatively has a significant impact on the final alignment of the system. So the plot on the left is the same simulation that I've been showing. It's a low mass disk, initially misaligned by 60 degrees, and the disk is moving towards polar alignment at 90 degrees. This is the longitude descending node, and the red line is the binary eccentricity vector. So you see that it's tightly coupled, it's oscillating about this eccentricity vector. Now on the right, this shows a higher disk mass, 0.05. So the same mechanism operates. Again, it begins at 60 degrees, but you see that the magnitude of the oscillations are much smaller. And the disk is actually oscillating about a much lower inclination of about 70 degrees. You'll also notice that the precession rate is much faster in this case. That's because the mass of the disk is causing the binary to precess in time. The separation of the binary is shown in the third panel. There's not terribly much evolution. But the eccentricity of the binary is changing. In particular, in the high mass case, it's oscillating, but it's also decaying in time. Okay. So we calculated analytically this stationary inclination. So by stationary inclination, I mean the inclination that this would align to over time. Okay, so this shows this inclination as a function of the ratio of the angular momentum of a third body compared to the binary. So this isn't actually for a disk, this is a third body, but it's a good approximation. So if we increase the angular momentum of the third body, or the mass of the disk, if you like, the stationary inclination decreases, as we just saw in the previous simulation. The different colors show three different binary eccentricity. Okay. Oh, and I should also point out, JJ also has a paper on this. Yeah. So I think he solved it numerically, right? Yeah. Okay. And then we can also calculate the critical inclination. So the inclination above which we would be in a librating state, so we process about the eccentricity vector, and below which we're in the circulating state, where we process about the angular momentum vector. So this is the upper line just shows the same that the stationary angle that I showed before, and the lower line shows the inclination between the two different states. This is the ratio of the angular momentum of the third body to the binary. So if we're below this critical inclination, then we're going to align to the binary. If we're above it, we're going to align to the eccentricity vector. Okay, so I'll just go back quickly to some of the observations. So 99 Hercules is a circumbinary debris disk that's observed to be polar aligned within a few degrees. So it's likely that a gas disk formed at some inclination. So the eccentricity is almost 0.8. So the inclination doesn't have to be very high for this mechanism to work. And then the gas disk is going to move to polar alignment, leaving behind any debris in this state. And then KH15D, roughly an equal mass. Well, this is a simulation for an equal mass binary. But the eccentricity is very high. It could even be up to 0.8. So if we look at even just the test particle orbits for such a high eccentricity, you see that the precession, these aren't circular. So the inclination is changing in time. So even in the case that this disk is moving towards alignment, it's not going to move towards alignment monotonically. There have to be large tilt oscillations during this process. So if the disk begins at 20 degrees, it can increase up to 70 degrees even during this alignment process. And then recently, this was the first observed polar aligned gas disk, HD 98800. It's actually a quadruple star. So there's two stars here and two stars inside this circumbinary disk. And this circumbinary disk is observed to be polar to the binary BB. The disk is relatively narrow, and so this is a likely mechanism that formed this polar aligned disk. Okay, so in conclusion, this polar alignment mechanism operates around an eccentric binary, so it leads to the alignment of the disk to the eccentricity vector. It operates for a wide range of parameters. The final alignment depends upon the mass of the disk. So if you have a very massive disk, the alignment could be 70 degrees. So then it's going to depend on where the debris ends up is going to depend on the timescale for the dispersion of the disk. So if the disk was dispersed very quickly and the debris was left at 70 degrees, then after this time, all the objects which just interact through gravity will just process on their own timescale. So you'll end up with a thick structure rather than a disk. So this could lead to problems for planet formation. But if the dispersion occurs more slowly, then during this time the disk could move to polar to 90 degrees, dragging the debris with it. So planets and debris disks around eccentric binaries may actually be more likely to be polar aligned than aligned with the binary orbital plane because of this process. So I just left a challenge. So how is this going to affect the planet formation process? Thanks for your time.
Thank you. Questions? Okay, we'll start with Jeremy this time.
Bit of a technical question. So these phenomena can all be sort of understood in a secular approximation where you average over the mean motion of the binary and the stream along the streamlines of the disk.
Mm-hmm.
But as I recall, slightly vaguely, in warped Keplerian disks, there's a kind of a resonance on the orbital period between the motion, the vertical motion of the warp with respect to the mean plane, and a sort of a sloshing mode, a radial epicyclic mode, goes in and out. This is studied by Papalouizou and maybe Terkem and others. And out of that, I remember there's some criterion that involves H over R and alpha that determines how serious this is. So the question is, with your SPH simulations, where alpha can't be really below 0.01, where are you with respect to this condition? And do you see these radial sloshings within they change sign across the midplane of the disk? The lower, say, when the lower half is going outward, the upper half is going inward.
No, well, I definitely don't see that in my simulations.
Maybe because your alpha is kind of large.
It's relatively large, yeah.
Okay.
I can't do small.
Well,
alpha.
just to say that there might be a different behavior, maybe a more rapid dissipation or something else in a low viscosity, if it is low viscosity PPD, it might be a qualitative change in some aspects of behavior.
Okay.
Look at those
JJ?
papers.
So the criterion is when H over R is greater than alpha? So So if I remember,
And I don't remember.
So and if I remember correctly from your simulations, usually alpha was significantly less than H over R. And basically, what happens, like those sloshing motions that you mentioned, that's when the bending waves can resonantly propagate across the disk. And when that criterion is not totally satisfied, instead of resonantly propagating across the disk, they locally damp. And that's when you get the different behavior. It's because they can't propagate across the disk anymore. All of the interactions are much more local towards where the warp is.
Thanks.
Any other questions? Yes.
So does this make any predictions for transiting circumbinary planets?
They should be there. Someone needs to find them. But I mean, obviously, it's more difficult because they're not going to transit every orbit. But yeah, I think they should be there. Especially now as we're finding polar-aligned disks. Yeah.
And I guess you're also making predictions for how they should be aligned with the rest of the system.
Yes.
Okay, if there are no further questions, let's please thank Rebecca again, and then we'll break for the coffee.